Is the universe expanding? This question was at the center of a controversial discussion held at Leiden University. The protagonists of our debate are none other than Albert Einstein and the Dutch astronomer and mathematician Willem de Sitter.
General relativity was formulated by Einstein, it's already a century ago. The universe is a very complex system, full of matter and structure. Motion of different planets, galaxies, etc. Depends on gravity, the force of gravity, but it's a very complex system. General relativity is a theory that describes gravity, and it tells us how space-time responds to matter. Finally, we were given a theoretical framework, a proper framework to study the universe and the phenomena that happen in the universe.
So Einstein's equations relate the geometry of the universe to its energy content.
Hey, no, not that one. Yes, this one indeed.
To Einstein, just because of what was known at that time, the universe had to be finite and static.
Einstein's equations predicted a universe that was not static. That's the reason why he came up with the idea of a cosmological constant.
So the cosmological constant is of course allowed, but the way Einstein used it was to indeed keep the universe static. If you want, it was put there by Einstein to match, but not really an observation, but an assumption that the universe was static, which at the time was sort of consistent with most of the things that they knew about the universe. He introduces the cosmological constants, but then he also realizes that this model of the universe that he created with matter, the cosmological constant, and curvature, spatial curvature, all arranged such as to give a static solution, really correspond to a static but unstable universe. So something that as soon as you would slightly perturb it, would run away from that solution. And so that to him was sort of a disappointment. And so that's when he sort of said, okay, then we are done with the cosmological constant. And also then eventually, of course, the expansion of the universe was detected. So he really concluded that he didn't need it. It's a space arena in which we are living and in which the galaxies form, etc., is expanding with time. So you think of galaxies as sitting in this spatial grid describing the universe. They will gradually recede from each other because this grid is sort of expanding. The first thing we observe is galaxies are receding from us, so the light emitted from them is redshifted.
Now follows a quick crash course on cosmological redshift. Let's say we look at the light emitted by a very distant galaxy. This wave will propagate through space. However, the wave stretches due to the expansion of the universe, much like what happens with this rubber band. De Sitter was the first one to propose a theory which elegantly describes an expanding universe. However, his brilliant idea was not accepted right away. He kept close correspondence with Einstein, in which he tried to convince him about the feasibility of an expanding universe.
So the De Sitter model, so while Einstein was trying to create a static solution to its equations once applied to describe the universe, De Sitter instead kept the cosmological constant, but didn't include any curvature and any matter in its universe. And he really looked at galaxies as sort of host objects in a universe. So if you want, a bit in a way that is counterintuitive to the whole concept of general relativity, where matter and space-time are really intertwined. So he really put only this cosmological constant, but that gave actually a universe that was expanding. Although for Einstein it was really a bit, he was unhappy with this setup of a universe just filled with a cosmological constant and matter just sort of passively moving because of what the cosmological constant was dictating to space-time. We know that then eventually Einstein and de Sitter formulated a different model of the universe. That was the one that then for decades was the dominant one. But eventually the Sitter model became popular for two reasons. One is inflation, and one is what we observe today, which is again a phase of accelerated expansion. So what you get out of the Sitter universe, the Sitter model, is not only an expansion, but an expansion which happens with an accelerated, with a rate that increases with time. And that is what we need to explain several observations at the very early phase of the universe, at the very beginning. And then now we know, since 2 decades, that we need it also at in the last few billion years of the universe. Yeah, this was a response to the observations, first to the Hubble measurement of the redshift of galaxies. So galaxies were receding from us with a velocity that was proportional to their distance. So Einstein was then ready to accept an expanding universe. So it thought, maybe I don't need any more this cosmological constant to keep it static. Also, there were no evidences for a curvature. So they said, okay, perhaps what we see is consistent with a flat geometry. And so they abandoned both things and they just put matter. Okay, we do and we don't understand the expansion of the universe nowadays, in the sense that 20 years ago we had these surprise measurements from supernovae that told us that the rate of expansion of the universe had started to increase again. So indeed we were expecting that after the initial burst and inflation, the rate of expansion would slow down. But then suddenly this expansion rate starts increasing again, and we don't have really good explanation for it if we stick with the laws of general relativity. So we tend to attribute this accelerated expansion to dark energy. And we are trying very hard to answer what dark energy is.